Welcome students. In this lecture, we will study about thermal expansion in solid, which is in your lesson number, which is in your unit number 7 of heat and thermodynamics. So, before going through the topic, let me just briefly tell you what heat is. Heat is a form of energy which causes sensation of warmness. Heat flow between two bodies take place as long as there is a temperature difference between them. So, there is a state known as thermal equilibrium where temperature of two bodies become equal. When this state is achieved, after that, no further heat flow takes place. So, now let us come to our topic, which is thermal expansion in solid. As you all know, when you heat an object, it expands. So, the expansion of a body under heating is known as thermal expansion in solid. In solid, three types of thermal expansion take place. If it takes place along one dimension, then this is known as linear expansion. If it takes place along two dimensions, then this is known as superficial expansion. If it takes place along three dimensions, then this is known as cubical expansion. Now, let us go through in detail one by one. In linear expansion or expansion in one dimension, only one dimension changes, that is length. So, if you consider a rod at 0 degree centigrade and L0 be its length, if you heat at T degree centigrade, the rod undergoes expansion and LT is the length of the rod at T degree centigrade. So, you can get here the increase in length due to change in temperature will be LT minus L0. It has been found that this change in length is directly proportional upon two factors. This LT minus L0 or the change in length depends on initial length, that is L0. This change in length also depends on rise in temperature, which is T. Now let us combine these two expressions. On combining these two expressions, we get LT minus L0 is directly proportional to L0 T. Now if we write, we can also write like this: LT minus L0 is equal to a constant of proportionality L0 T. Here, alpha is a constant of proportionality known as coefficient of linear expansion. So, alpha here is coefficient of LT minus L0 alpha times L0 T, or we can write LT equal to L0 plus alpha times L0 T. In the RHS we can take L0 common, and now we have this expression. So this is the expression of length of the rod after expansion. Now we can also find out the value. We can give an equation. From this equation, we can find out the value of alpha. Now we can find out alpha will come LT minus L0 divided by L0 T. So this is known as coefficient of linear expansion. We can find out from any equation. We can find out from this equation also. We can find out from this equation. So alpha or coefficient of linear expansion is defined as increase in length per original length per unit degree rise in temperature. Okay. Now we'll move on to expansion in two dimensions or superficial expansion. If a body expands along two dimensions, then this is known as superficial expansion. That means length and breadth. Now suppose this is a thin sheet having area is 0. if you heat at T degree centigrade, then the sheet expands and St is the final area after heating. So from this we can find out St minus S0 will be your increase in area after expansion. It is found that this increasing area also depends upon two factors. So this increasing area depends upon initial area. It also directly depends upon rising temperature T. Now combining these two above expression, we can write St minus S0 directly proportional to S0 T, or St minus S0 equal to beta times S0 T. So this is your expression for increasing area after expansion. Increasing area after expansion. Here, beta is constant of proportionality. Which is known as coefficient of superficial expansion. From this equation 1, we can also find out the value of St. So here St will be S0 will go to the right hand side, so it will become S0 plus beta times S0T. Now, from both these terms, we can take common S0T. So now, the equation will reduce to St equal to S0 1 plus beta times T. So this equation 2 is an expression for increase in area after expansion. So now we can also find out the value of beta, that is your constant of superficial expansion. We can find out from equation 1. So the value of beta will be St minus S0 divided by S0T. So beta will become St minus S0 divided by S0T. So this equation 3 is the expression for beta or coefficient of superficial expansion. Now let us come to expansion along 3 dimensions or cubical expansion. Now let us consider this smaller cube which is at 0 degree temperature. So the volume of the cube at 0 degree temperature is of course V0. Upon heating at T degree centigrade, the cube expands to volume V of T. So now, the increase in volume will be Vt minus V0. It has been found that this increase in volume due to change in temperature is directly proportional upon two factors. So this increase in volume is directly proportional to initial or original volume V0, and also it is directly proportional to rising temperature T. Now combining this above two equation, we can get Vt minus V0 is directly proportional to V0, or we can write Vt minus V0 is equal to gamma times V0 T. This is equation 1. So this equation 1 gives the expression for increasing area after expansion. Now here gamma is a constant of proportionality which is known as coefficient of cubical expansion. Now from the equation 1 we can find out the value of, from this equation 1 we can find out Vt equal to V0 plus gamma times V0 T. RHS we can take common V0 this equation 2 represents the volume of the cube after expansion. Now we can find out the value of coefficient of cubical expansion gamma. Now from equation 1 we can find out the value of gamma. So gamma will come as Vt is V0 divided by V0. So using equation 1 we find out the value of gamma, that is coefficient of cubical expansion. Now let us find out the dimension of alpha, beta and gamma. So we have found out the value of alpha is Lt minus L0 upon L0. So in the numerator we have the dimension of length. So it will come as L1. In denominator we have L0 and T. So the dimension of L0 is simply L. In the dimension of here T is temperature, which is represented as K. So this L1 and L1 will cancel out and we will have the dimension as like this, K to the power minus 1. Similarly, the dimension of beta will be St minus S0 divided by S0. So the dimension of area we know is L2 and the dimension of S0 is L2 and the dimension of T is K1. The dimension of beta is also same that of alpha, which is K to the power minus 1. Similarly, we can also find out the dimension of gamma, which is V3 minus V0 divided by V0 T. So this will be also. So from this equation we find out the dimension of alpha, beta and gamma is same, which is K to the power minus 1. Now let us derive the relationship between the expansion coefficients alpha, beta and gamma. Let us first find out the relation between. Now consider a thin sheet at 0 degrees centigrade. So L0 is the length of each side of the sheet. Now S0 is the area of thin sheet. So we know the formula area will come out to be, so S0 will be L0 into L0, which is L0 square. Now let us give this equation as equation number 1. Now if we hit the thin sheet, so it will automatically undergo expansion. Now if Now on hitting, the length of the sheet becomes LT and ST is the area of the sheet after expansion. The area of rod at T degree centigrade will be LT into LT, that is L square. Take this will be equation number 2. Now we know the expression of coefficient of superficial expansion, that is beta equal to ST minus S0 divided by S0T. Now what we'll do is we will substitute the value of S0 and ST using equation number 1 and 2. So we will have beta equal to LT square minus S0 square divided by S0 square into T. Now we know LT equal to S0 into 1 plus alpha T. This we have derived earlier. Let this be equation number 3. Now we will substitute the value of LT in this above expression. Now the above expression will become beta will be S0 1 plus square minus S0 square divided by S0 square T. So it will become S0 square 1 plus alpha whole square minus S0 square divided by S0 square T. Now we can take common S0 square from the numerator. Now we can cancel out S0 square both for numerator and denominator. See, here we have the form of a plus b whole square, and we can write like this: 1 plus alpha square t square plus 2 alpha t minus 1 divided by 2. Here plus 1 and minus 1 will cancel each other, so the equation will be like this: alpha square t square plus 2 alpha times t divided by t. Now taking common t for numerator, we can write alpha square t plus 2 alpha divided by t. So this will be alpha square t plus 2 alpha. We have taken the assumption, we take the assumption that if the value of alpha is very small, we can neglect higher order terms of alpha. That means we will only consider the power 1 of alpha. We neglect the powers beyond 1. So the equation will reduce to beta is 0 to alpha. Thus we will find out the relation between two expansion coefficients alpha and beta. Now we will find out the relation between alpha and gamma. Now let us consider Q at 0 degree centigrade. So L0 will be the length of each side of Q at 0 degree centigrade. So the volume of Q at 0 degree centigrade will be, this volume of the Q will be your L0 into L0 into L0, that is L0 Q. This is the question number 1. Now, if we heat the cube, it will undergo expansion. Now, LT will be the length of length of each side of cube after expansion. Similarly, Vt will be your volume of cube after expansion. So Vt will be your Lt into Lt into Lt, that is your Lt cube. Now you know the value of coefficient of cubical expansion, comma, that is your Vt minus V0 divided by V0 T. Now what we'll do, we'll substitute the value of Vt and V0 using equation 1 and 2. Now let us substitute value of Vt and V0. So this will become Lt cube minus L0 cube divided by L0 cube into T. This is equation number 3. We know the value of Lt, which is your L0 plus alpha T, which we have derived earlier. Now we substitute the value of Lt in equation number 3. Now let us substitute. Now the equation will become like this: L0 1 plus alpha T cube minus L0 cube divided by L0 cube. So this is of the form of a plus b whole cube. So this will be 1 plus alpha cube a cube plus 3 alpha square t square plus 3 alpha t. Now we can take L0 cube common from the numerator. So this will become 1 plus alpha cube t cube plus 3 alpha square t square plus 3 alpha t minus 1 divided by L0 t. Cancel out L0 cube from the numerator. Now the equation will be used as, we can also cancel out plus 1 and minus 1. Now the equation will be like this: alpha cube t cube plus 3 alpha square t square plus 3 alpha t divided by t. Now we can also cancel out t from both the terms. So this equation will reduce to alpha cube t square plus 3 alpha square t plus 3 alpha. Now we take an assumption that we will neglect the higher order terms of alpha. We will only consider the power 1 of alpha. We will neglect higher order terms of alpha. So here we will neglect the first and second term. Only the third term will remain. So the equation will reduce to alpha equal to 3 times alpha. We have found out the equation between, the relation between the expansion coefficient alpha and beta. Now we find out the relation between expansion coefficient gamma and alpha. Now we can find out the relation between the expansion coefficient beta and gamma. Let us find out. So we had beta equal to 2 times alpha. So let us directly find out the relation between alpha, beta and gamma. So it will be like this: alpha is to beta is to gamma is to become alpha, and we substitute the value of beta, that is 2 alpha, and value of 3 alpha from gamma. So this will be like this. So this will be in the form of alpha. We cancel out from all the terms. So this will be 1 is to 2 is to 3. This is the relation between the expansion coefficient